Namaste, welcome to Pythagoras Academy. This is Vikram Dachepally. What if two springs are connected in series or parallel? What is the effective spring constant? So I am going to derive the effective spring constant if the springs are connected in series or parallel. Let us first take the series combination of the springs. Series combination is one spring is connected to the other in serial, one after the other. So if two springs are connected in series, say a mass m, a load is applied on these two springs. Now if you look at the free body diagram of this mass, it has got its weight mg down, and the extension in the spring, let it be x1, so k1 x1. Let the extension in the spring of spring constant k2 be x2 and the extension in the spring of spring constant k1 be x1. So the effective stretch of two springs combined would be x1 plus x2. It means if the mass m is lowered to come to equilibrium, it would come down by x1 plus x2. The meaning of effective spring constant is, instead of having two springs, what if I replace these two springs set up with a single spring? What is that K effective? Which gives the same effect, which behaves the same way when the load of m is applied to it. In the sense, for this K effective, if m mass is attached to the spring, it is coming down by effective stretch of x1 plus x2. So in this case, x effective is equal to x1 plus x2. Now mass m, mg, and in the upper direction it is K effective into x effective. That is the net spring force. So this K effective into x effective is balancing mg. So mg is equal to K effective into x effective. So x effective is equal to mg by K effective. Here kx1 is equal to mg. Now x1 is equal to mg by k1. You can expect a different kind of question from this series combination of springs in competitive exams. That if two spring balances are connected in series to a mass m, what will be the reading of these two spring balances? Will it be equal or unequal? As you observe, the reading of the first spring is k1x1, which is equal to mg. Now observe this point. This point is being pulled up by k2x2. It is being pulled down by k1x1 because there is a stretch in both the springs. When the springs are stretched, the spring force will be in the direction of pull. Now this point is in equilibrium, so I can say k1x1 is equal to k2x2. The fundamental thing, the fundamental concept, that if two springs are in series, then the spring forces in two springs will be equal is applied here. You can clearly see that spring forces in two springs will be equal. So k1x1 is equal to k2x2, that is equal to mg. So from this I can also write k2x2 is also equal to mg. Now if two spring balances are connected in series, each spring balance will give the same reading, which is equal to reading of this mass m or the weight mg, because k2x2 is also equal to mg. So x2 is equal to mg by k2. Now x effective is x1 plus x2, which is equal to mg by k effective. Now x1 is mg by k1 and x2 is mg by k2. That is equal to mg by k effective. So from this I can say that 1 by k effective is equal to 1 by k1 plus 1 by k2. So if two springs are in series, then k effective can be written as k1 k2 by k1 plus k2. Suppose if 3 springs are in series, then 1 by K effective is 1 by K1 plus 1 by K2 plus 1 by K3. In that case, K effective would be K1 K2 K3 by K1 K2 plus K2 K3 plus K3 K1. So this is the standard equation to find the effective spring constant if 2 springs are in series. Similarly, let us also derive the expression of effective spring constant if K1 and K2 are connected. Or if 2 springs of spring constants K1 and K2 are connected in parallel. Parallel combination is where two ends are connected to one common point, that is ceiling. The other 2 ends are connected to the block. So as you see on the screen, this is the parallel combination of springs. In this case, if the stretch in the first spring is X, then the stretch in the second spring is also X. So the mass would be lowered down by X units in order to come to equilibrium. Then the free body diagram of M, it has got weight, it has got K1x and K2x. So K1 plus K2 into X, that is equal to mg. Now if 2 springs are connected in parallel, then the stretches in 2 springs would be same. If 2 springs are connected in series, we have seen that the spring forces in 2 springs are same. But if 2 springs are connected in parallel, spring forces in 2 springs will be different, but the stretches in each spring would be same. So now what is K effective? Instead of having 2 springs, if I have to replace this setup with a single spring of K effective, so that it is also being elongated by a same amount of X for the applied load M. In that case, so the free body diagram is mg down, the spring force is K effective into X. So K effective into X, that is equal to mg. So now from these 2 equations, I can clearly write that K effective is K1 plus K2. So if 2 springs are in parallel, the effective spring constant is the sum of the spring constants. If 3 springs are in parallel, then K effective is K1 plus K2 plus K3. If n springs are in parallel, then K effective is K1 plus K2 plus K3, so on up to Kn, that is sigma K1. So this is the result of parallel combination of springs. So we use this series and parallel combination especially in while dealing with the oscillations. So if a block is connected to set of springs and it is slightly disturbed from the equilibrium position, it oscillates. So to find the time period of oscillations, getting the effective spring constant will help us solve the problem easily. So that is all about series and parallel combination of springs. Thank you. If you have any questions or queries or suggestions, you can always use the comment section to interact with me. I'll be more than happy to respond and receive your feedback. This is Vikram Dachepally signing off. Namaste.